Good day, everybody. Today I want to look at 5 integrals from the Berkley 2021 final round of their Integration B. Came across this video, watched it, struggled with a lot of these, pretty much all of them, and decided to work them out, and there was some interesting math, so I decided to present this. So these are the 5 integrals, and of the 2 finalists, neither one got the first 2, and then somebody got each of the last 3. And so I'm going to look at these in reverse order. The last one's the only indefinite integral, so there's the integral. So the solver got it before I did, but after the fact it's not too bad. You've got these 4 terms, and you also have an x. You can easily cancel, and it really doesn't matter if you cancel first or later. I'll leave the x's alone for now and factor the denominator by grouping. So in the end I kind of want to factor out x cubed, but let's pretend like we didn't know that yet. So I'll just factor out x squared, and then we would have 1 plus x arctan x, and then we can factor out an x to the 4th here and get the same thing in parentheses, 1 plus x arctan x. And so while we can factor what's in the parentheses out, it's common to both terms there, and so then we'd be left with x squared plus x to the 4th. So we're getting close to where we want to do our substitution. If you try u equal this, it won't quite work. So what I'll do is I'll bring this x in as a, like, it's a 1 over x in the denominator. I'll go ahead and change it right here. So if I distribute the 1 over x, then I get this. And we could have gotten this in other ways. I could have, you can see the denominator here, I could have factored x cubed first from the first 2 terms and x to the 5th from the second 2 terms, and then I would have a 1 over x plus arctan x common to both, and then I'd have an x cubed plus x to the 5th, and then you can cancel the x. Or if you cancel the x first, then I'd have to factor out an x squared. Right, if I have an x plus x squared, and if I have an x cubed plus x to the 4th, I'd have to factor out the x to the 4th. So there's lots of ways to get to this, and then that's it. So this will be the u, and we'll just have to see how it works. Du will be negative 1 over x squared plus 1 over 1 plus x squared dx, which is, if you get your common denominator, negative 1 plus x squared plus x squared all over x squared times 1 plus x squared, which is what I have right there in the denominator. And then if you distribute, you just get negative 1. The x squareds will cancel. So I'll just put it this way. Negative du is 1 over, and if I distribute, okay, so I have a negative 1 on the top, but I'll multiply both sides by negative 1, and so you have that. So we can see we have a 1 over u times negative du. So negative natural log u, so negative natural log of 1 over x plus arctan x, and then plus c if you like. Oops. So there's that result. And let's look at then the 4th one, going in reverse order. So this integral. So I won't rewrite this one. Key here is, let's let n be a specific value. Let's let n equal, say, 100. Then the integrand is the min of 2, or the max of 4 minus x over 100. And if you plot this until you reach 200, this is bigger than 2. Okay, so at 200, that's when it equals 2. If you're less than 200, then 4 minus x over 100 is going to be bigger than 2, right? Like if x is 100, this will be 3. If x is 0, this is 4. So the graph is 2. So since this is bigger, the min of 2 and this is going to be 2 until you reach 200. And then after that, now this will be smaller, and it'll reach 0 at 400. And this is 2. And so the min of 2 and this, whoops, I forgot the 0. There it is. So I need that 0. So once you reach 0, then the max of these two will be 0, and then so the min of these two will be 0. So this will be the full graph. So this has area 400, base times height, and then this is a triangle with exactly half that area, base, height, 1/2. So this has area 200. So altogether, a equals 600. If you divide by n, we get 6. And well, that was for n equals 100, but it's not too hard to see that regardless of n, the same thing's going to happen. So here's the plot with n equal 100. Again, base times height, 400, and then this is exactly half that, so 400 plus 200 divided by 100 is 6. But regardless, you can let n be bigger or smaller. If n is 10, then now this has area 40, base times height, and then this will have area half that, so 20. So that's 60 is the area, divided by n is again 6. N could be 1, it doesn't matter. If n is 1, now it's 4 plus 2, 6 divided by 1. And n can be any value. We're actually always going to get 6. So that's that result. Again, so it's a little tricky because you're integrating to infinity, but most of it's 0. So I mean, you want to fix an n first, find this result in terms of n, and then take the limit as n goes to infinity. But each integral gives the result 6, so then it's the limit as n goes to infinity of 6, which will be 6. All right, this third one. Now, someone did get this one. I don't know if they did a lucky guess, but I mean, some clues would be if it's on the integration B, I mean, it has to be doable. A quick look at the answer. It's going to boil down to 1 over a quantity to a power plus 1 over a quantity to the negative power plus 1 always equals 1. Okay, so the integral is not symmetric, but with opposite x values, they're going to add up to 1, and opposite x values for the square root are identical, So you're just going to basically get double the area under a quarter circle. No, not double. You're just going to get the area under a quarter circle. Maybe should have said half the area of a semicircle. To see this, get your common denominator. You get u to the minus p plus 1 plus u to the p plus 1 divided by, and then if you multiply these, this times this will give you 1, and then outer, inner, and last, and that equals 1. So that's somewhat the key, but how do we see that we have something to a power and something to a negative power? So you have to know a little bit about cosine and cosh. Cosh is defined as e to the x plus e to the negative x over 2. We don't need sinh, but put it there for completeness. And so that's the definition of cosh. You might know e to the ix is cosine x plus I sine x, and that would lead to e to the negative ix is cosine x plus I sine x. Just put a negative I in for I, or a negative x in for x, and then cosine's even, it absorbs it, and sine's odd, it would factor out. So if you add these two together, the signs cancel, and you get 2 cosine. So if you add these two together and divide by 2, that's another way to get cosine. If you were to subtract, you would get the cosines canceling, and then you'd have 2i sine. So if you divide by 2i, that will give you sine. But again, we don't need that. Anyway, so we can then see from this definition of cosh and cosine that cosh of ix, if I put an ix in for x, would be cosine. And kind of conversely, if I put an ix in for x in cosine, then here I'd have I times ix, which would be negative x, and here I'd have negative I times ix, which would be negative I squared, which would be positive x. So it'd be the cosh, it'd be reversed. You'd have e to the negative x plus e to the x, but addition is commutative. So those two things would switch. So these two things are true. And again, we don't need the sign, but this would be the case for sine and sinh. Anyway, so for cosine of root x, we would get cosine of root x when x is positive, of course. But if x is negative, then cosine of the square root of a negative, well, it's kind of like an I times the absolute value of x, or the negative of x, if x is negative. So in other words, we'll get the cosh of negative x, and when x is negative, that's a positive value, or cosh of absolute value of x, if you want to look at it that way. So this is what the graph will look like. And cosh of root x is cosh of root x if x is positive, but it's the cosine of negative x if x is less than 0. Okay, so that's from these identities, right? So you would get an I here. If x is negative, you can, and then think of x as negative 1 times negative x, and the square root of the negative 1 is the I, and then the negative x is right here, and then just use these identities. And so if we look at cosh of square root of a negative plus cosine square root of a negative, that's going to end up being cosine plus cosh, or in other words, the same thing. The order gets switched, but addition being commutative. So the sum is going to be commutative and equal. But the difference, which is the exponent of our integral, cosh minus cosine, if you sub in a negative in for the argument inside the square root, it will switch signs. So if I want to see how that helps us, again, now we would have integral -1 to 0 square root of 1 minus x squared all over, just for simplicity, I'll just write the parenthesis, and then to the power, I'll just put p, and then dx plus integral from 0 to 1 square root of 1 minus x squared, and then there was a plus 1, and then of course the same thing. And now we're going to do a substitution on this one. I guess I'll use t. So let t equal negative x, or negative t equal x. So negative dt equals dx. And so the limits on this second one will be from 1 to 0, but I'll have a negative, and I'll have the square root of 1 minus t squared. And I'm too much here, but what's here is that sum, and so if you put a negative t in there, it switches the order, but it's otherwise the same. But the power reverses. So that's what this is, and then we're going to add it to that. Now this negative will switch the limits, so we essentially just have the integral from 0 to 1. Whoops, I put dx here. I guess it would be dt, but then I'll switch it to a dx as a dummy variable. So anyway, so 1 minus x squared, and then basically, as I said, u to the negative p plus 1 over u to the p plus 1 dx, and that became 1. And so this is a little bit hand wavy, but anyway, so pi over 4. So hopefully that was clear enough. Maybe one more look at some of the identities here. Another thing that I noticed a long time ago but didn't think too much of because my graphing calculator won't graph cosine of root x, but if you know the power series for cosh and cosine, then you can easily plug a square root of x into them, and well, it looks good for all x. Right, so here it looks like the domain should be x going from 0 to infinity, but here it doesn't. One other thing before we look at the graphs, notice, I mean, you can see the concavity at 0, nice and simple. It's positive for cosh, but negative for cosine. It's concave down at the origin. But for square root of x, cosh, concavity at the origin, well, it's still positive, but now cosine switched to positive as well. That's interesting, and we'll see. And then here's the power series for the sum and difference. Just if you add them, the odd terms cancel, so you get double the even, or if you subtract them, the even terms cancel and you get double the odd, except the subtraction becomes addition, so it looks like that. Having the software look at this, here's the definite integral, 0.45, which is over half of pi over 4, and then there's the integral from 0 to 1. Right, so it wasn't symmetric. If I look at the graph of cosine of square root of x, then on the right hand side it's cosine, but on the left hand side it's going to be cosh, hyperbolic cosine of square root of x, which is, you might know, is kind of U-shaped and so forth. Got so like this. So cosine of square root of x is on the right, so it's a cosine function, but since it's square root of x, it stretches way out. So it's cosine being stretched way out because it's the square root of x. But on the right hand side it's hyperbolic cosine of square root of x. I'm sorry, that's the left hand side. On the left hand side it's hyperbolic cosine of square root of x. Right hand side cosh. And then cosh is going to be the opposite. So cosh will be cosh on the right, but on the left it's cosine of square root of x. There's the function, and here's the area we're finding. Whoops. So we're finding the area under this shape. Interesting shape. But again, the key idea is that for this function we're multiplying the square root by. So here I factored the square root out. So here the square root's in there, and so of course here's 0 at the endpoints of plus or minus 1. But without that square root, opposite x's always add to 1. You can see that with this graph. So you can perhaps see that opposite x's will always add up to 1. Look at this symmetric graph. And that was the key idea. So then if you multiply that by square root of 1 minus x squared, opposite x's, I mean if I compare to the actual circle, are going to add up to what the quarter circle would be. And incidentally, so this exponent, it could have gone the other way. You could have cosine minus cosh, because that would be the same thing. The shape would just flip. So this also has area pi over 4. So there's that result. Getting closer to the end here. This one wasn't too bad. They were close. Does need one fact that isn't too common. So the key idea on this one is that the integral of a sum will be the sum of the integrals. That's always true for finite and for infinite. This is actually absolutely continuous, so there are some theorems about when you can change the order of integration and summation, but here we can. So I'll change it to a sum of integrals, and this is a constant with respect to x, so I can factor that out. So we just need to integrate all these signs. We'll just do a nice substitution. U equals 2n plus 1 over 2, and then x, whoops, and then du is 2n plus 1 over 2 dx. So 2 over 2n plus 1 du is dx. And then my integral, I'll just look at this integral. It's going to be the integral from 0 to 2n plus 1 pi of sine u du. Oops. And then I've got this constant out front, 2 over 2n plus 1. And we can either do the integral. I'll leave that to you. I'll just do it by reasoning out that I know like when n is 0, I'm integrating from 0 to pi, and the integral of sine from 0 to pi is 2. But if n is 1, I'm going from 0 to 3 pi, which is 0 to 2 pi, and that'll be 0, and then pi more. So it's pi more than 2 pi. So it's like integrating from 0 to pi. And so that'll be 2. And if I integrate, if n is 2, that's 5 pi. So that's 0 to 2 pi twice, and then 0 to pi one more time. Right? 0 to 5 pi twice around the unit circle and once more. Or I guess thinking of the sine wave, 0 to 2 pi, that's 0. 2 pi to 4 pi is 0. And then 4 pi to 5 pi will be the same as 0 to pi. Anyway, so this will be 2 for all n. And we got this out front. You could do antiderivative, but let's argue this way. So now I'm going to multiply by 4 over 2n plus 1 times this, and I'm going to flip this up, and there's a 4 over 2n plus 1 being squared right here. So if I flip that up, I got 2 times 4 times 4, and I got 2n plus 1 cubed on the bottom. So if I put this in for the sign, 4 over 2n plus 1, I'll get 2n plus 1 cubed, I'll get a 4, a 2, another 4, and a negative 1 to the n. And so if I write out what this is, since that's cubed, this is 32. And then when n is 0, I get 1 over 1. And then minus 1 over 3 cubed, plus 1 over 5 cubed, minus 1 over 7 cubed, and so on, all the odds. And that actually equals pi cubed over 32. So that's not too well known, so I don't know if that was supposed to be known or what. I'll look it up real quick here. So there's our rule that we need, some others. I also want to look at that integral in a different way. The integrand is a sum of sine functions, which you might know is kind of a Fourier series way of representing functions. So here's the sum from n equals 0 to 4. Keep it small for now. And if I look at the plot of the function, it looks like this, almost triangular. Let's put in a few more terms, well, many more terms. Let's go to 40. And notice the base is going to be 2 pi. The height will be pi squared. So the area of that triangle, 1/2 base times height, is going to be pi cubed. And that would be the integral of the function, the area of that triangle. Let's do a few more here. I go to 400. There's the plot. And notice, so if I evaluate the function at pi, we've been getting closer and closer to pi squared for the peak. So maybe one more here. 4,000. Take 4,000 terms. And we're getting even closer to pi squared. So the more terms I take, the closer we'll get to pi squared at the peak. If you just go to infinity, then you get essentially a perfect triangle. If I plot over a bigger range, say negative 12 to 12, why not? Then that's the Fourier series. Again, base 2 pi, height pi squared. Integral is the area under the triangle. 1/2 base times height is pi cubed. So that was our penultimate integral. Sorry. Now comes the last integral. And this is the one that sort of gave me the most trouble, so I left it to be done last. So let's take a look at it. First thing we might recognize is that we've got this difference, a sine A cosine B minus sine B cosine A. So that can be written as sine of A minus B, which I did. And now the argument of the sine function, I can get in the denominator if I factor out an x squared. So I did that, and so you can kind of see a sine u over u, but we have this x squared in the denominator in a dx, so it's not quite perfect, as we'll see. It's also an even function, so we might consider doubling and going 0 to infinity, but that actually didn't seem to help me. So the way I ended up going, I did have to break the integral into 2, as we see, but not doubling, at least not yet. So if I break the integral into 2, I've got the integral from negative infinity to 0 plus 0 to infinity, then we're going to need a substitution. U is the argument of sine, 2x minus 1 over x. Du will be 2 plus 1 over x squared dx. And so you get that 1 over x squared, but we get this 2 really throws things off. I simplified this to 2x squared plus 1 all over x squared dx. So this is what I need for du, so I just put it in there, 2x squared plus 1 over x squared. I slid the x squared over, but I can't change the problem, so essentially I multiplied and divided by 2x squared plus 1 on both integrals. And so I'll redo that u substitution. U is 2x minus 1 over x. So I'll have sine u over u, and this will be du on both integrals. But I've got this 2x squared plus 1. And I could not see a tricky way to get rid of it. So in the end, got a little brute force action. So if u is 2x minus 1 over x, then let's solve for x. You can multiply through by x, and get a quadratic, and then use the quadratic formula to get x is u plus or minus the square root of u squared plus 8, all over 4, and that's a 4, not a u. To make sure of that as we continue. Now I knew from up here, this is going to be 0 at x equals root 2 over 2. And negative root 2 over 2. So at x is this value, u is 0. So let's look at x a little bigger and smaller, then we'll go with a positive root 2 over 2. So I mean that's roughly 0.707-ish. So if x is 1, then u would be 2 minus 1, which is 1. And so it's going to turn out we need the positive root here for if we're bigger than 0. Right? So if u is 1, we would get 1 plus the square root of 9, which is 3. So 1 plus 3 over 4 is 4 over 4. So x would be 1. So that checks out. Well, what if we're on the other side of 0? U being 0. So what if we're at, say, 1/2? If x is 1/2, this will be 1 minus 2, which is negative 1. And this still works. So if I plug negative 1 in here, it's negative 1 plus the square root of 9. That's a u squared. So negative 1 plus 3 is the square root of 9. So negative 1 plus 3 is 2. 2 over 4 is 1/2. So we want the positive root for all positive values of x. And also if we look, as x goes to infinity, of course this goes to 0, so u will go to infinity. And as x goes to 0 from the right, this goes to 0, and this will go to minus infinity. And so this is what it's going to be for positive values of x. If u is 2x minus 1 over x, that's the same as x is u plus the square root of u squared plus 8 all over 4. You take the positive root. So that works for the positive x. And u has to go negative infinity to infinity to get the full range of x going 0 to infinity. For the negative x's, well, let's see, all right, not yet. So, and then here's the limit. So the limit is that u goes to negative infinity. This will be 0. If there's a linear term, that would affect the limit, but with no linear term, usually I didn't show this, but you could easily show it. I usually multiply top and bottom by the conjugate, and then you can simplify things. But so this will essentially be like negative infinity plus infinity that goes to 0. And this obviously goes to infinity. So as u goes to negative infinity to infinity, we get all the x's from 0 to infinity. And for the negative x's, that's when we want the negative root here. And u still go negative infinity to infinity. Right, so as u goes to negative infinity, x will go to negative infinity. X is this, so x will go to negative infinity. If u is negative 1, x will be negative 1. If u is 0, x will be negative root 2 over 2. And if u is positive 1, we would get negative 1 minus root 9. So we get negative 1/2. And as you keep doing bigger and bigger u's, you're going to approach 0 from the negative side. So like if u is 1,000 minus the square root of 1,000,008 that's almost 1,000. It's actually slightly bigger, so this would be just almost 0 but slightly negative. And the bigger u is, the closer you get to 0. So to recap, for positive x, u is this, the positive, so 2x squared plus 1 is going to be 2 times this squared, and if you square this, first squared, 2 times this, plus the last squared, divided by 16, but times 2, left me with 8, and then plus 1, so bring it in as a common denominator, and now you have u squared plus 8, and another u squared plus 8, so 2 u squareds plus 8s, and 2 this, so cancel those 2's, leaves me with this. And for negative x, 2x squared is going to be this, but with the minus. And same idea, if you square it and add 1, we'll get almost the same thing, but with a minus here. So we get that. So looking at this integral again, there it is again, u is going to be this argument, which is also that. Du will be this. And then 2x squared plus 1 for the negative x is going to be u squared plus 8 minus the square root divided by 4, which I flipped over. And as x goes negative infinity to 0, u has to go negative infinity to infinity. And similarly over here, that's u divided by u, there's du, and then 2x squared plus 1 is all this, divided by 4, flip it up. X go negative infinity, or 0 to infinity, means u goes negative infinity to infinity. So then I've got these two integrals I'm adding together. I can write them as 1, factor the sign u over u out, and I'm left with this plus that, get a common denominator. It'll be 4 times this plus 4 times that divided by the product. Now the product, I probably should have put parentheses here on the u squared plus 8 on both of them, but it'll be, this is like a minus b times a plus b, and it'll be a squared minus b squared. So if you think of u squared plus 8 being in parentheses, you got the first, then outer, inner, will end up canceling, then the last squared. So we'll get that. And so what's our numerator? It's 4 times u squared plus 8 twice. So that's 8 times u squared plus 8. We also have a 4 times this positive quantity and 4 times the same thing but negative. That'll cancel. On the bottom, we've got a u squared plus 8, which I can factor out. I can now cancel that, and I'm left with u squared plus 8 when I factored out the u squared plus 8, and minus u squared, and then the u squareds cancel, and you're just left with 8. So these cancel, and you have 8 over 8, which is 1. So I just have sine u over u, and again, this is even. So now I doubled it. Twice 0 to infinity, so that's sine u over u, just 2 times pi over 2, or pi. Now you had to know that one result. It's somewhat well known, but maybe among the winners of the Berkley integral contest, although they didn't get this one, but that was tough to even get that far. But like, so various integrals. So there's that one integral. So you had to know a few things to do all these integrals. All right, so we've got trouble with these integrals. The real trouble is at 0. It's going to blow up there. So I kind of kept away from 0. If you look at the graph, you can see, so as you go to 0, you're blowing up. So the integral doesn't exist. Well, its absolute value would not be integrable, which means technically it's not Lebesgue integrable. But if you looked at the limit where a was bigger than 0, then let a approach 0, that limit would exist, because what you add, you keep adding and then subtracting almost the same amount, and what you add and subtract does go to 0, so you're not going to vary. I don't know if that makes sense, but you're going up and down so fast, the area under any pair of consecutive zeros is going to get smaller and smaller, even though the peak is going to infinity. So we're adding something but then subtracting almost the same thing, and then adding again and subtracting. So it's not going to change too much from here, this 0.022, you know, we're already close to pi over 2. Also notice we don't necessarily have to be under. In fact, actually we're over, and if I get closer to the origin, then we go down. I picked that value just so that would happen, but so it actually got lower. But that's just because it's oscillating, so you can't tell if you're going to be above or below the true value. But anyway, so what we add and subtract is going to 0. So anyway, the limit does exist. Here's the curve. As you get farther away from the origin, then everything's better, right? This is bounded by 1, and this is going to infinity, so everything will be great. There's a little trouble at root 2 over 2. It's a removable discontinuity. The y value is 2, and I plotted, so that would be right there, but everything's fine. So the limit, it's a removable discontinuity at root 2 over 2. If I look at the plot of u equals 2x minus 1 over x, here's the plot. I plotted in a few points. Let me zoom in on them. Root 2 over 2, 0, and negative root 2 over 2, 0, 1, 1, and negative 1, negative 1, and 1/2, negative 1, and negative 1/2, 1. So I plotted those points. So for positive x, here's u equals 2x minus 1 over x. And if I solve for x, I need the positive root. Have it this way. And you can see u needs to go negative infinity to infinity to get all the positive x. And for negative x, for u equal 2x minus 1 over x, if I solve for x, x is u minus the square root. So it looks like that. So that'll give me all the negative x. Again, u needs to go negative infinity to infinity to get all the negative x. And finally we get our integral, and I had to double that. So there's our last result. Alright, so those were the integrals. It was not easy, but nothing worth having is easy, as they sometimes say. So hope you enjoyed that. Keep doing math. Thanks, and have a good rest of your day.